Now let's look at the backward algorithm for HMMs. The backward algorithm. So we define a backward variable beta as follows. Beta Ti is the probability of the future outputs Vt plus 1 to Vt given state St equals Si. So this is what it looks like visually. This is the future output beta Ti accounts for Vt plus 1 to Vt given the current state St equals Si. Now let's compare it with the forward variable that we had seen earlier. So alpha Ti is the forward variable, and that's probability of V1 to Vt. It accounts for the outputs from the past until the present and St equals Si. This is the difference. They kind of complement each other. By definition, beta T plus 1j, now the present pretended to be T plus 1, so the future starts from T plus 2. So beta T plus 1 comma j accounts for the outputs Vt plus 2 until V uppercase T given St plus 1 is Sj. And we will derive using beta T plus 1j, we will derive an expression for beta Ti, which is given by this probability. So this is where we start from, and this is what we will eventually arrive at. So beta T plus 1j is the probability of Vt plus 2 to Vt given St plus 1 equals Sj. This is of this form, probability of C given B, where C is Vt plus 2 to Vt and B is St plus 1 equals Sj. Now let's multiply it with Pij. Pij is, by definition, probability of St plus 1 equals Sj given St equals Si. That's the transition probability from Si to Sj. And that's of this form, Pb given A, where B is the same as before. The same B is this, probability of St plus 1 equals Sj, and A is St equals Si. So the product from Bayes' rule gives you this. Probability of C given B, probability of B given A equals probability of C comma B given A, which is equal to this expression here. Probability of Vt plus 2 until Vt, comma St plus 1 equals Sj given St equals Si. And that's the product of this beta T plus 1j and Pij. Beta T plus 1j and Pij. And why do we get this? It's straight away from this expression. C is the same as before. It's Vt plus 2 to V uppercase T. B is, as before, St plus 1 equals Sj. And A is, as before, St equals Si. So this is what we got. Next step, let's multiply it with Qjvt plus 1. And on this side, I have this. Vt plus 2 to Vt is this, and now the Vt plus 1 has been added, and that's because of the emission probability. So QjVt plus 1 is the probability of emitting Vt plus 1 output when St plus 1 is Sj. And St plus 1 is Sj is now part of the left side of this conditioning, and we can get rid of it by doing the summation over all possible Sj's. So this is the summation, and the summation will get rid of this St plus 1 equals Sj, whence we are left with probability of Vt plus 1 through Vt given St equals Si. And this is by definition equal to beta Ti. So backward algorithm, we have the definition of beta Ti, and that accounts for all the future outputs time t plus 1 onwards given St, the current time step. The state is Si. Now, what's beta uppercase Ti? T is the last time step. Since beta accounts for the future sequence of outputs, if we are at the last step, there is no other sequence left. So beta uppercase Ti is equal to probability of null, because we have already reached the last step uppercase T, and there is no future Vt plus 1. Vt is the end. So this is null given the last time step St equals Si. And the probability of null is always 1. Probability of nothing to happen is 1. Nothing will always happen. Beta Ti is equal to summation j Pij Qjvt plus 1 beta t plus 1j. We just derived this recursive expression. Now, what's probability of Vt equals 2 to Vt given S1 equals Si? That's beta 1i. All I've done is replace t with 1, and so t plus 1 becomes 2. The future starts from time step 2. So beta 1i is given by this probability here. Whence probability of V1 through Vt given S1 equals Si is equal to beta 1i times the emission probability, Qi, comma V1. So the difference is this. We account for V1 by multiplying the emission probability. Whence, now what I've done is, in the next step, this bold V is the entire sequence. I have taken this condition S1 equals Si and moved it to a joint probability. So PV comma S1 equals Si. And how is that accomplished? This is the difference. The condition above is moved to a joint event, and that's because I multiplied it with pi I. Pi I is the probability of S1 equals Si. And then I do the summation over all possible Si's here, and I get P of V equals this summation over all possible i's of this quantity here, which is pi I, qi v1, beta 1I. So that's how I get P of V, the probability of the given sequence V. I have to use beta 1I. Okay, so these are the different components of the backward algorithm. So we just saw that beta uppercase Ti is 1. That's our initialization. And then we use this recursive rule to get beta Ti from beta T plus 1j. So we are going backwards in time steps. T plus 1 is given, and then we obtain T. And at the end, when we obtain beta 1, then we are in a position to compute the probability of the entire output sequence V. So visually, this is what happens. We begin with beta uppercase Ti, and this is equal to 1. So we initialize all of these betas for all the different states to be equal to 1. And then we proceed backwards. Suppose at time step T plus 1, we have beta T plus 1j. And that accounts for the future outputs Vt plus 2. Using this recursive rule that we just obtained, we will get beta Ti from all the beta T plus 1j's. And that accounts for up to Vt plus 1 future. And then we proceed until we hit time step 1, where we have beta Ti's for each of these states. And then we apply this expression to get P of V from the beta 1i's and q's and pi's. So here's the algorithm, the backward algorithm. We initialize beta uppercase T I to 1 for all states I. And then we begin the backward recursion. Each time step we take beta T plus 1, and using this expression we get beta T, and at the end we compute PV from beta 1i's. Now what's the time complexity of backward algorithm? Let's look at the main component. The outer for loop will iterate T times. The middle for loop will iterate for every state, which is N times, and the summation will be carried out again for N times steps. So the complexity of backward algorithm is order N square T. The end.